In proving the variational principle, we used a technique that's often used in quantum mechanics where we express a trial function as some kind of linear combination over a set of eigenfunctions. And this may have seemed unusual at the time, but in fact this is something that is done quite a lot. And let's talk a little bit about what this means and how one can use this to our best advantage. Well, first of all, I'll note that the point of expressing functions in terms of other functions should be one that we're eventually getting used to a little bit. And what do I mean by that? Well, for example, we could take a function and express it as a power series. For example, we could write it something like this. And from mathematics, we know that we can express each of these coefficients in terms of that original function as follows. The coefficient corresponding to the kth term would be 1 over k factorial, the kth derivative of our function f of x with respect to x, and this derivative then evaluated at x equals 0. We're effectively expanding this function about x equals 0 in terms of these polynomials, in terms of these powers of x. But these powers of x are themselves functions of x, right? So for example, I could define f0 of x is just equal to 1, and f1 of x is just equal to x, and f2 of x is just equal to x squared, and so forth. And so in effect, what I've done is I have taken my arbitrary function f of x and expanded it as a series of different functions of x. Right? That's sort of a liberal interpretation of that. But let me give you a more specific example that is actually a very powerful one in physics and in physical chemistry. And that is something called a Fourier series. I mean, let's suppose that you have a function that is some kind of oscillating function, but it's not a simple trigonometric function like you're used to. All right, well, it turns out that you can express functions in terms of sines and cosines as follows. If I have some oscillating function, I can write it as a constant. And I'll just, for various reasons, I'm going to write the constant like this, plus the sum over a series of terms. And let's say, for example, it's a finite series, but it can in principle be infinite. But it's a finite series, and each term looks as follows. We have a coefficient a sub n times cosine of nx plus another coefficient b sub n times sine of nx. And it turns out that we can represent just about any oscillating function in terms of a series that looks like this. So look what we're doing. We're taking a function and we're writing it as a bunch of terms that are a weighted sum of sines and cosines. Now these sines and cosines vary because the n here causes each cosine function to be different from every sine function, or different from other cosine functions within this summation. Now, just as we have a simple formula for the coefficients of a power series, we actually can formulate expressions for the coefficients of a Fourier series. So, for example, the nth coefficient a is equal to 1 over pi times the times the integral of minus pi to pi of our function f of x times cosine of nx. And our coefficient b is just 1 over pi minus pi to pi of the integral f of x sine of nx dx. All right, so we have a way that we can readily calculate these coefficients. We can express f of x as this interesting combination, linear combination of functions of cosine and sine. Well, when we generalize this, we can use essentially any set of functions like this. We typically try to choose functions that have special relationships to one another. For example, that they're orthogonal to one another over a particular interval in coordinate space. And for this reason, using the eigenfunctions of a Hermitian operator are particularly advantageous. Remember, for Hermitian operators, we have the following. We have, for example, that their eigenfunctions So maybe I should write specifically the eigenfunction relationship. Okay, so these are the eigenfunctions of the Hermitian operator A, but these form a complete set. And I'm going to put this in quotation marks, not because it's not really complete, but because complete means something very special mathematically in this case. It means that they are a set of functions that actually span the space. In other words, any function on that same spatial interval can be represented as a linear combination of these eigenfunctions. All right, so one of the reasons that it's especially useful to use eigenfunctions of a Hermitian operator is because we know that, for example, their overlap is going to be 0 if m does not equal n. And if we normalize these functions, it will equal 1 if m equals n. So we're typically going to make use of the fact that the eigenfunctions of a Hermitian operator are orthogonal, and if we normalize them, this is something that we will actually come to call orthonormal functions. Orthonormal set of functions. And these are extremely useful when we want to express any arbitrary function that is going to be based on the same part of space. So that means that any function f of x that is well behaved, and when I say well behaved, I mean it is smooth, it is continuous, it has a continuous first derivative. So all of the things that make a wave function be a valid wave function for matter and quantum mechanics. So if f is a function like that, then we can write it as follows. We can write it as a series of these eigenstates. And in some cases, this series is a finite series, but in many others, it's an infinite series. So we just tend to write this using a summation sign, n equals 0 to some unspecified number, a sub n, psi sub n of x. So we can express these functions, any function, like this. And if we were to multiply this function, so let's say we multiply on the left side by psi m star, and then integrate, what we would end up with is as follows. We would have integration over all space, psi m star times the sum, let's make this of f of x is equal to, and then I'm going to use this sum over on the other side, so I'll have the integral psi m star of x and now I can bring this inside here and write this as the sum a sub n of these integrals but I know that, and I should have had dx here, but I know that if they're orthogonal, they're going to be orthogonal if they are eigenfunctions of a Hermitian operator. So this is going to force us to say m is equal to n in this summation, so this is just equal to a sub m. So look, a sub m is now defined by this integral of the mth eigenfunction f of x integrated over all space. So we're going to be using these kinds of things in several different areas in this course, but this is something that was used to prove the variational principle, and it can be used for many other purposes as well.